Professor Williams Phillips. Please.
Thank you very much, Rector, and thank you, Pavel, for that kind introduction. I'm hoping that I can share my screen now. Okay, are you seeing the slide?
Yes, it's okay.
Wonderful. Okay, well, thank you very much for that kind introduction. I'm very pleased to be here at this conference, albeit remotely. I'm going to talk to you about the reform of the International System of Units, the metric system. And this is an appropriate topic for any scientific gathering because everyone measures things. And the system of units that we use to measure things is something that has been evolving according to the scientific and technological needs. And I want to point out, as has already been mentioned, that NIST and the National Scientific Center Institute of Metrology are sister institutes, national metrology institutes of our respective countries. And I also want to, I'm having a hard time advancing the slides. I also want to mention that I'm giving this talk under the auspices of the International Union of Pure and Applied Physics, which was a major force in the creation of the International System of Units and continues to promote the reforms that have been made. And finally, I must say something that I'm honored to say, but I wish that I didn't have to say, and that is that while I'm honored to be here, that I have to recognize that there is this ongoing and brutal war against Ukraine, and to all of the students in the audience who are continuing their education, to the faculty members and the researchers who are continuing to teach and to mentor the next generation to try to make this world a better place through scientific discovery. Your courage and your perseverance are inspirational to me, and I believe to all the world. The United States, our allies, and our partners around the world are united in our support of Ukraine in response to Russia's unprovoked and unjustified war, and the continued bravery of the Ukrainian people in defending your sovereignty, your territorial integrity, and democracy is an inspiration to all of us. So on to the talk. The metric system came into being with the French Revolution at the end of the 18th century. And on the 20th of May, 2019, which is World Metrology Day, we have experienced the greatest revolution in measurement since the French Revolution. And that is a revolution to the International System of Units, the metric system, and to its base units. Everything in the metric system is based on 7 base units: the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela. Everything that we measure, every other physical quantity, is based on those 7 base units. And what we have done in the recent reform is to define each one of those base units by defining a constant of nature. And this talk is about how that is done and why it had to be done and what are the results. So in order to see how it can be done, that is, how it's possible to define a unit of measurement by defining a constant of nature, I would like to give you what I'm calling a brief history of time, with apologies to the late, great Stephen Hawking, who wrote a book of that title. For a very long time, almost since we started to think of time in terms of seconds, a second has been the duration of one day divided by 24 hours per day, 60 minutes per hour, and 60 seconds per minute. The trouble is that since about 1900, we have known that this day changes. It's not just a matter of the day length of the day changing throughout the year, even averaged over the year, what we call the mean solar day. The length of the day is changing because of the friction of the tides, because of redistribution of ocean currents, because of redistribution of mass, because of of earthquakes, the length of the day changes. Yet the rotation of the Earth is defining what we mean by 1 second. And that seems like an intolerable situation. We can't have a standard of measurement as fundamental as the second changing. Well, there are better clocks than the Earth. The first clock, so-called atomic clock, actually a molecular clock, was made at NIST, or at the National Bureau of Standards, in 1949. By 1955, at the National Physical Laboratory in the United Kingdom, they had made a cesium clock. And cesium is still today the atom that we use to define what we mean by time. Well, how do these atomic clocks work? Well, here is a very oversimplified version of how an atomic clock works. Imagine a cesium atom with a valence electron and a nucleus, and the electron and the nucleus are spinning, and the orientation of the electron relative to the nucleus can change. There are two different possibilities corresponding to what we call the hyperfine states. And the energy separation between those two states is about 9 gigahertz. If you shine in microwaves at a frequency of 9 gigahertz, about 9 gigahertz, if it's just right, then it will cause the atom to change its state. It'll cause the electron to flip its spin. But when the frequency is not just right, then it will do nothing. And so the way an atomic clock works in this oversimplified version is you tune the microwave frequency until the electron spin flips, and then you know that you have the right frequency. And this is that right frequency. We have defined the hyperfine frequency to be this. The official definition of the second in 1967 was that the second is the duration of some 9 billion periods of the radiation corresponding to that hyperfine transition, and that is equivalent to defining what the hyperfine frequency is. Here's a plot of how good these atomic clocks are as a function of time. And you can see that over time, they keep getting better and better. By the mid-1990s, these clocks were better than 1 part in 10 to the 14. But we wanted to do better. And the performance of these clocks was stalled at about 1 part in 10 to the 14, mainly because the cesium atoms are moving so fast. These are thermal atoms, a little bit hotter than room temperature, and even an atom as heavy as cesium is moving faster than 100 meters per second. This makes it difficult to measure the transition frequency of the cesium atoms for many different reasons, and I hope you'll ask about them during the question period. But this motivated us, and in particular in my own research group, to develop the technique of laser cooling, which was able to slow the atoms down to only 1 centimeter per second by cooling the atoms below 1 microdegree above absolute zero. And that improved the performance of these clocks to a few parts in 10 to the 16. And here is a photograph of one of the cesium clocks with atoms that are cooled to below 1 microdegree above absolute zero and keep time to a few parts in 10 to the 16th. This is the most accurately measured quantity in the International System of Units. The key concept here is very important. We went from something that is rather arbitrary, namely the rotation of our own planet, something that is not constant, something that can change for any number of reasons. And we have replaced that with a quantum transition in an atom, something that, as far as we know, is constant in time and constant throughout the universe. Now, an even better story, a short history of length. Time was really important historically, but length was even more important because it involved things like commerce and construction. And the early approach to length was to use the human body as the standard. A foot was the length of a foot. A cubit was the distance between one's elbow and the tips of the fingers. Well, this was really convenient because you always had your standards of measurement with you, but it wasn't very consistent. If you were buying fabric, for example, from a short fabric merchant, you might not get the amount of fabric that you were hoping for. So one approach to this inconsistency was to make a particular body, typically the king or the monarch, to be the standard of measurement. This was the approach used in ancient Egypt. The length of the king's forearm was used to define what was called the royal cubit. Now, the trouble was that the pharaoh was not generally available. If you're building a pyramid and you want to measure how big the blocks should be, the pharaoh is not necessarily at hand. And so they made a standard, a primary standard in stone that was itself the length of the pharaoh's forearm. And here is a replica of that Egyptian cubit. And then the engineers out in the field who were doing things like building the pyramids used wooden versions of this standard, and they were required to calibrate them against the stone standard at least once a month. And the penalty for not calibrating was death. These people were extremely serious about their metrology. And the results were fantastic. The baselines of the pyramid are consistent to a small fraction of a percent. The pyramids are square to 12 arc seconds. These are really well done feats of engineering, and it was accomplished because of seriousness in metrology. Well, the idea of using an artifact standard for length was something that was continued in more modern times. Throughout Europe, there were similar artifacts, varying often from one town to the next. Sometimes to encourage commerce, they were set in stone in the town square. Here is a picture of the standard fathom in the town of Regensburg in Germany. And you can see, compared to this tourist, that the fathom in Regensburg is quite generous. But if you were to go into a town in surrounding Bavaria, you would likely find a very different standard for the fathom. Well, the French revolutionaries decided that they would fix this, that they would come up with a new standard of length, which they called the meter, that would be available to everyone for all time and for all people. They defined the meter to be 1/10,000,000th of the distance between the pole and the equator along a meridian that goes through Paris. And this meter was to be the measure of all things. They made these commemorative medals to illustrate the idea. And you see this mythological creature, in a sense, measuring the earth. And that's exactly what they did. They sent out surveyors to measure the distance between Dunkirk and Barcelona and extrapolate it to the full quarter meridian, and brought those measurements back to Paris after many years of work in the field. And then what they did was very similar to what they did in ancient Egypt. They used these measurements to make an artifact. And here's a picture of that artifact called the Meter of the Archives. It was deposited in 1799 at the end of the 18th century in the archives of France, and it became the standard of length for France and for all countries who subsequently adopted the metric system. In 1875, there was an international meeting at which the nations who were gathered in Paris adopted a treaty called the Convention du Mètre, promising to use the metric system for their own measurements in the country, and promising to establish an international bureau of weights and measures that would make a new meter and keep that meter and disseminate it to the rest of the world. Well, here's a cartoon picture of the new meter. The distance between these two scratches was made to be as close as possible to the end-to-end length of the Meter of the Archives. And that became the standard of length for the entire world. Now, it is near the end of the 19th century in France, and physicists have learned that light is a wave, and they have made instruments called interferometers that can measure distance in terms of the wavelength of light. this cartoon of an interferometer, a Michelson interferometer, and Michelson, the American physicist, was the first one to measure the wavelength of light in terms of the meter in the BIPM, in the International Bureau of Weights and Measures. And the way it works is that light comes in and is split on this beam splitter between one beam that goes to this movable mirror and another beam that goes to this fixed mirror. And then the light is reflected back and recombined. And the two paths, the one that went to each of the two mirrors, recombine. And because the light is waves, when the waves line up, we get a bright spot. And when the waves are out of phase, we get a dark spot. And when you move this mirror just 1/4 of a wavelength, which is approximately 2/10 of 1/1,000,000th of a meter, you change from light to dark. So you now have a way of measuring lengths to a tiny fraction of a micron with a standard of length that is based on two scratches, and the scratches are tens of microns in diameter. So you can see the problem. You have a definition of length which is not as good as the technology by which length can be measured. And so what happened was, for many decades, people were using the wavelength of light as a sort of de facto standard of length, not the true legal standard of length of the international metric system, but one that was better and used as a matter of practicality. It took many decades until 1960 to redefine the meter in terms of the wavelength of light. And here is a picture of a lamp that is filled with krypton gas, and the orange light coming from this lamp is the light whose wavelength was used to define what the new meter was. But 1960, as mentioned here, was the year in which the laser was invented. And soon lasers like this, a helium neon laser, stabilized to a transition in molecular iodine, were much better than the krypton lamp. So once again, you had a situation where the technology for measuring length using laser light was much better than the definition of length using the wavelength of a krypton lamp. And so for years, people used lasers like this one and interferometers to measure length. So it was clear that once again, we needed to redefine what we mean by a meter. The obvious choice would have been to redefine the meter in terms of the wavelength of this iodine stabilized helium neon laser. But fortunately, the metrologists of that time did not make the obvious choice. Instead, they made a beautiful and brilliant choice. They defined the speed of light. The new definition of the meter was that the meter is the length of the path traveled by light in vacuum during a time interval of 1/292,792,458. In other words, this number was now defined as the speed of light in meters per second. And you see the beauty of this. If you can measure the frequency of the light, and by 1983, when this definition was made, we had learned how to measure the frequency of light. If you measure the frequency of light, and if you define the speed of light, then this universal expression that the wavelength times the frequency is equal to the speed of light tells you what the wavelength is. To whatever precision you can measure the frequency. And that means no matter what kind of light you have a ruler that is calibrated because of the fact that you've defined the speed of light. And so if somebody comes up with a better way of measuring the frequency of light, and they did, or if somebody comes up with a better laser that has a more pure wavelength, and they did, and here are some of the people who did that. Jan Hall and Ted Hensch got the Nobel Prize in 2005 for doing just that, making better lasers and making better frequency measurements on those lasers. Those improvements were already built into the definition. And so this business of going from an artifact, a piece of metal that defines the length of the meter, to an atom like krypton, and finally to a fundamental constant of nature means that we should never need to change the definition again. Now, this definition of the meter is, in my opinion, both beautiful and brilliant, even more beautiful than the definition of the second. And in 2019, the international metrology community brought this same kind of beauty to the kilogram, and for that matter, to the ampere, the Kelvin, and the mole. So now I want to explain why this was necessary at this time and how it was done. And for that, I'm going to give you a light history of mass. Here is a photograph of some polished stones that were used in ancient Babylonia as mass standards. They might have been used to calibrate the weight of precious metals that were used in coins. One of these stones, I don't remember which one, is called a shekel, a word that you might have heard. The trouble with these, of course, was the trouble with all such standards. They might vary from one place to another. And consistency was something that was lacking in this ancient way of determining weight. And so the French revolutionaries decided that they would solve the problem of the inconsistency of mass standards in the same way that they had solved the problem of length, namely to use the meter, the measure of all things, to create a new standard of mass. So what they did was they defined the mass of 1 liter of water, which is 1 decimeter, a cube, 1/10 of a meter on a side. They defined the mass of 1 liter of water to be 1 kilogram. Well, this is wonderful. Everyone has water. The meter is the new standard of length. It seems like a great choice. But it turned out that it wasn't very easy to get exactly 1 liter of water, and it wasn't very easy to determine what the mass of that water was compared to metal mass standards. And so, once again, these metrologists made an artifact. And here am I holding that very artifact, the 1799 kilogram of the archives. I'm actually holding it in my hand, or at least I'm holding the case. This became the definition of the kilogram for France and for the rest of the world that adopted the metric system. And with the 1875 Convention de Mètre, a new mass standard was made called the International Prototype of the Kilogram. You can see it here under 3 different glass globes. And this was the artifact that defined what we mean by a kilogram for the entire world. And it's the last artifact. This is the definition of the kilogram up until 2019. The kilogram is the unit of mass. It's equal to the mass of the International Prototype of the Kilogram. Well, what could be simpler than that? The trouble is that it's really not a very modern definition, and it's not a very useful definition because of its inconsistency, its variability. The idea that in the 21st century, that the unit of mass is a piece of metal that was made in the 19th century based on an object made in the 18th century is really scandalous. Think about it. If someone leaves a fingerprint on the International Prototype of the Kilogram, all of us would lose weight. This is not a tolerable situation. Well, nobody leaves fingerprints on the International Prototype of the Kilogram, but it's clear that its mass is changing. Here is a plot of the mass of the International Prototype of the Kilogram, symbol K, compared to a number of other identical kilograms made at the same time. And they all start off the same. Well, there were slight differences that were calibrated out. And over time, they diverged. Now, of course, when you see this, mostly diverging in the same direction, it's hard to not conclude that the International Prototype of the Kilogram is changing. But of course, by definition, it cannot, because it is always a kilogram. So we have to change things. What shall we do? We want to fix the value of a fundamental constant. What constant shall that be? Well, to explain, I want to remind you of what is probably the most famous equation of all history. E equals mc squared. The energy of an object is equal to its mass times the square of the speed of light. Another equation, not quite as famous, is that the energy of a photon, a particle of light, is Planck's constant times the frequency of the light. If we combine the two equations and solve for the mass, we find that mass is equal to Planck's constant times frequency divided by the square of the speed of light. Well, what does that mean? It means that if I had an object like a nucleus and it emitted a photon, a gamma ray, and I could measure the frequency of that gamma ray, if I define the Planck's constant, and I have already defined C, it means I know what the change of the mass of that particle is in kilograms. Now, this would be essentially weighing a photon. We can do that, but not well enough. And so we have another method, still using the idea that we define Planck's constant, that can get us a kilogram to the precision that we need. Imagine an atom. We shine a laser onto the atom. We know what the frequency of that laser is, and that means we know its wavelength, and we know the momentum of the photon. It's Planck's constant divided by the wavelength. The atom is excited by this photon, but it also absorbs the momentum of the photon, so that means the atom is going to recoil with a velocity that's equal to Planck's constant divided by the mass times the wavelength. If we can measure that velocity, and if we define Planck's constant, and if we know the wavelength, which we do, it means we now know the mass of the atom in kilograms, not in atomic mass units, but in kilograms. Now all we need to do is to multiply that up to a large enough number that it's useful. And this is done by making a near perfect sphere of silicon. The semiconductor industry has learned how to do this over the years, and you can make essentially a perfect crystal that is a perfect sphere. And as a result, you measure the dimensions of the sphere, and because you know that it's a perfect crystal, and you can measure the crystal lattice spacing, you know how many atoms are in that sphere, and we know the ratio of the mass of silicon to the mass of, for example, rubidium, which means we know the mass of that sphere. It's not an artifact. It's a way of constructing what is exactly a kilogram. And this is one of the ways in which we can realize the definition of the kilogram. I don't have time to tell you about another wonderful way in which we measure the kilogram using an electromagnetic balance, but let me just show you a picture of it. This is a balance at NIST that measures the kilogram using electromagnetic forces instead of atomic physics. And it, along with other experiments all over the world, can realize the kilogram to about a part in 10 to the 8th. And in fact, laboratories all over the world did exactly that, using the silicon sphere method and using the electromechanical method. They all measured Planck's constant first, because that was the idea, was to turn the experiment around, using this to measure Planck's constant, and then finally to reverse the process, define Planck's constant, and use this to realize the kilogram. Well, when all of these laboratories agreed, the General Conference of Weights and Measures met in Paris, and this was the movie they showed after the vote that redefined all of these constants.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta.
We have a special holograms.
Lei sia boli.
Biz bundan ayrı olduk.
Proud died.
Biz bunu жасадық. Het is ons gelukt.
Un tasarım.
Vi gjorde det. Amerika, ja.
My jsme to učinili.
Dokázali jsme to. Congratulations. Felicitaciones.
Mazal tov.
Congratulazioni.
Shate lavorisce.
Salamat. Success.
Parabéns.
Ongela.
Omedeto.
Kamsahamnida.
Onneksi olkoon.
Mabruch.
Kapai.
Aiko.
Félicitations. Congratulations.
Well, whenever I see that movie, I'm really moved that 60 countries in the world could unanimously agree on something as difficult as this. And it's the way things ought to be handled internationally, not the way some countries handle their relationships with others. Well, it's not just the kilogram that was redefined. The ampere was defined by defining the charge of the electron, so that an ampere is now a certain number of electrons per second. The mole is no longer an amount of substance with the number of entities equal to the number of carbon-12 atoms in carbon-12. Now we have defined the Avogadro constant, and a mole is simply something that has this many entities. The Kelvin used to be 1/273.16 of the triple point of water. Now it's defined by defining the Boltzmann constant. I love this definition because it really speaks to the atomic and quantum nature of what temperature is all about. Well, it appears that we've really done what the ancient French revolutionaries hoped for, that we've got a system that is good for all time and for all people, except for one problem, and that is that we now still define time in terms of a specific atom, cesium, rather than in terms of a fundamental constant. And so we still need to redefine the second. And this is under consideration at the moment. And as for the future of time itself, only time will tell. Thank you very much.
Thank you very much, Professor Williams Phillips, for your very interesting presentation. And now, have you any questions to Professor William Phillips? Dear colleagues, dear participants, please.
Good day, dear colleagues. So, can I ask a question? Yes?
Please.
Yes.
Thank you. Thank you, Professor, for the report on behalf of all young scientists of National Technical University Kharkiv Polytechnic Institute. This is really a great question on the border of scientific areas and new epochs, and it's very important to do new scientific achievements. But there is also one open question about metric system. A few days ago, I had some discussion with my colleagues about this. And of course, first of all, we are scientists, but also we are lecturers or future lecturers, and science does not stand still. Also, physics the same regardless of the time. But there are new methods, new discoveries that must be introduced into some educational processes. How do you think? How can quantum reform affect education and training? In your opinion, of course, are there opportunities to introduce new units definition into curricula and materials, as well as challenges associated with preparing teachers, lecturers, and students to understand new science and use new unit system in education, in lectures, and so on, so on, so on. Thank you for your answer.
Yes, you've asked a very good question, and one that a lot of us have been puzzling over for some time, because obviously in the old way of doing things, it was relatively easy to tell a young student, a kilogram is the mass of a liter of water, or a kilogram is the mass of this object that is kept in a vault outside of Paris. And now we are faced with the difficulty of making a young student understand a kilogram is the mass that makes Planck's constant equal this value. And that does not seem like a very intuitive way of explaining what a kilogram is. So my own opinion, and I'm not sure that it's a very good opinion. I think we have to find out what actually works in the classroom. My opinion is that we should first introduce the old ideas, which are more intuitive, and then explain that modern technology has demanded that we go beyond those old ideas to more modern ideas, and then introduce these more modern ideas at whatever level is understandable to the students. We may not be able to introduce the idea of the recoil of a single atom and how it might be measured to elementary school students. But perhaps we can introduce the idea that light itself has a mass associated with it, and that the kilogram is related to the mass and the momentum of these particles of light. But I agree with you. This is a real challenge, and I think it's one of the things that we look forward to good teachers coming up with good ways of transmitting this new concept to our students. I think it represents a real challenge for teachers.
Thank you. Have you any questions to Professor Williams?
Can I ask some question?
Okay, please.
Dear Professor Williams, Phillips, thank you very much for your interesting report. And I have a question. In your opinion, should we expect a significant change in the system of units in the future? Or will only some adjustment in the form of prefixes be added periodically?
Yes, thank you. That's an excellent question. Except for the unit of time, I'm hoping that all the other units will remain unchanged forever. This was the motivation. This was the hope in defining things in the way that we have defined them, that we should never need to change again. Now, of course, there's always progress, and it might be that a new scientific discovery will reveal a different way of defining one of the units of the SI that will be better than what we are using today. But at least as far as what we understand today, we should not have to change any of the definitions except for the definition of time. Today, we have atomic clocks that operate at optical frequencies. So instead of operating at 9-point-something gigahertz, these clocks operate at close to 10 to the 15 hertz. Now, that higher frequency means that they are much less susceptible to a number of perturbations. And so these clocks are much better than the microwave clocks, which means that we need to redefine what we mean by a second. Those clocks today are good to a part in 10 to the 18, whereas our microwave clocks are only good to a part in 10 to the 16. Now, you may say, well, that's really good, but we always want to do better. So I expect that the next major change in the system of units will be a change in the definition of what we mean by a second. Now, you also mentioned about prefixes and suffixes. As we go to more extremes of the very small and the very large, then we run out of names. And so, as you've noted, we've come up recently with some new names for what some of these higher order and I don't even remember the new ones. What, 10 to the minus 24 and 10 to the plus 24 have new names. And this is, I consider to be a minor change in the international system of units. It doesn't really change anything. It just makes it more convenient for people saying the names of things.
Thank you. And second question, should we do something in the case when one unit describe different values? For example, inverse second can describe the frequency, hertz, and becquerel, the unit of radiation. Should we do something in this direction, or the situation is not important?
Well, you've touched on an extremely sensitive subject, and in fact, this exact subject is under active consideration by the international metrology community at the moment. It is tied up with the question of how we treat the radian, because of course another way of expressing frequencies besides hertz is in radians per second. And the trouble with radians is that sometimes we drop it out of our expression of units. And so we have sometimes an ambiguity. That is, the unit of hertz is, as you said, expressed as 1/seconds. But the unit of radians per second is also expressed as 1/seconds. And then you have an ambiguity of a factor of 2 pi. My own opinion is that when you express a frequency, you should always say what quantity you are measuring per second. So you should never say that the frequency is just a number per second. You should say it's hertz, which we understand to mean cycles or revolutions per second, or it's radians per second, or it's possible that you could use degrees as a measure of a frequency. But you should always say, in my opinion, you should always say what that actual unit is explicitly. Now, becquerels, of course, is another issue, and decay rates, for example, even when they're not becquerels, because becquerels is only for radioactivity. But, for example, the decay rate of an optical transition is something that we measure in per second. And sometimes people get confused and say that those things are hertz, but hertz is only to be used for periodic phenomena, not for stochastic decay processes. So, as I said, you've touched on an extremely sensitive subject, and I wish I knew a really good answer to it. I think the best answer is that everyone who expresses anything in print has to be very careful to be extremely explicit about what you are saying. The problem is this, that today we have information that is being read by computers, not by people. And computers are not yet very good about using judgment. And therein lies one of the problems that you have exposed, is that how do we solve these problems without relying on human judgment? And the answer to that is something we're working on. We don't have a good answer yet, I don't think.
We have one question from chat. Please, just a minute, please.
We have one more question from Maxim Malovica. How can we measure 1 meter with the help of nanometer lasers?
Yeah. Well, basically, it's done interferometrically. Now, if the wavelength, now, a typical wavelength that you're going to use, you're not going to use X-rays or far ultraviolet. You're going to use visible light, unless there's some reason why you need to measure something better than that. For example, LIGO, which measures the laser interferometer gravitational observatory, the gravity wave observatory, uses visible light to measure distances that are a fraction of the of the diameter of a nucleus. So visible light is very good for doing these kinds of things, and much more convenient than using shorter wavelengths. So you're probably going to be using light that has a wavelength of hundreds of nanometers, and you're going to use an interferometer. Now you might say, well, how do you measure a meter when the wavelength is, say, 1/2 millionth of a meter? Well, fortunately, in modern times, we have the ability to count how many fringes are being passed, and it's not so hard to move a meter and count every fringe. In the 19th century, this was a real problem, and people had to multiply up shorter lengths where they could count the fringes to longer lengths, and it was a really difficult problem. Today, we just count the number of fringes, and it's relatively easy. Modern technology has made this a much easier problem for us than it was for people like Michelson back in the 19th century.
Professor William Phillips, thank you very much that you take part in our conference and for your very interesting report. Thank you very much once more.
Evgeny Ivanovich, may add one very small addition for this. May.
Okay,
1 minute.
short edition.
Of course, it's deal with the question raised Ksenia about the meteorological. I want to announce that with a colleague from Kharkiv University Polytechnical Institute, we publish 2 books, study books, which deals with introduction to quantum metrology. It is both collective from part of the Kharkiv Polytechnical Institute and my National Scientific Central Institute of Metrology. And of course, these books teach and very useful for teach the student about the new quantum metrology. The first question, and second, I want to also promote my institute because we are in 16, 17 participate in this very fundamental experience to recognize the speed of light. And our results were published in Kadata research, and my institute also mentioned the results. And in this case, I want to mention that, of course, our international cooperation and maybe with NIST cooperation should be developed more ethically in future to develop this new quantum standard. I will be very appreciated. It will be possible for the future between our institutes. Thank you so much.
Wonderful. So get those books, and I look forward to cooperation between our institutes as well.
If you don't mind, Professor Williams, Kharkiv Polytechnical University won't continue to work with you and, of course, with Professor Nezhmakov in future. It's very interesting for us and, of course, for our students and for our teachers and for our scientists. Thank you very much once more.
Absolutely.
Thanks.
It's been a pleasure.